Good morning, everyone. I am Saurav Mishra, a PhD student from the Artificial Intelligence and Robotics Laboratory, headed by Professor Suresh Sundaram at the Indian Institute of Science, Bangalore. I work on multi-label learning, continual learning, spiking neural networks, and physics-informed neural networks. Today, I will be presenting our paper on improved imbalance resilience in continual multi-label classification with adaptive margin spiking neural networks, which was done in collaboration with Dr. Shirin Dora from Loughborough University, UK. We are grateful to IEEE SMC for accepting our paper and giving us a chance to present our work. Here is a brief outline of today's presentation. We begin with the introduction and motivation and review the associated literature in the domain with some focus on bipolar neural networks. Then, we discuss the proposed adaptive margin spiking neural network architecture and the proposed loss function. Then, we touch upon the experimental settings and discuss the results. Finally, we end the discussion with conclusions and future works. In the real world, data can belong to multiple categories. For example, the show shown below falls into three categories shown below. Similarly, the shoes here fall into the categories shown below. Multilabel learning studies this problem of mapping data into a set of categories. Samples can be shared across categories. Also, the labels can increase with time, as in the case of the number of COVID-19 variants. Thus, it is important to study continual multilabel learning problems. The objectives are outlined below. The models should be able to learn from a stream of samples and labels without forgetting the old ones, and should not use any buffer of previously stored samples from past data. We also assume that the old labels remain unchanged while new ones can arrive with time. Also, we do not deal with hierarchical categories in this work. Continual learning for multiclass data and multilabel learning have been well studied separately. While continual learning problems for multiclass data can learn from a stream of samples and labels, they may not adapt to multilabel learning scenarios where there is usually more data imbalance. For example, the plot below shows the number of samples for each label in the G-negative dataset, making the data imbalance across the labels apparent. Traditionally, the binary cross entropy loss function is used for classification. However, it does not distinguish between the samples based on how well the model learns it. As a result, the data imbalance adversely affects the model performance. To counter this effect, the focal loss function weights the positive and negative parts of the BCE loss function differently. As a result, the model incurs very low loss values on samples on which it is more confident, making these samples less important for learning. Continual multilabel learning is relatively less studied. Two noteworthy works in this domain, along with some of their key features, are mentioned below, namely deep streaming label learning and continual and interactive feature distillation. Some challenges are mentioned in bold below. The data division often leads to some samples with all negative labels in some tasks, making learning very challenging. This can be seen from the example of the G-negative dataset. To learn from such samples in continual multilabel learning, the bipolar networks and its extension to spiking neural networks have been proposed. Bipolar networks, as shown here, have two parallel output layers after the feature extractor unit. The loss function for bipolar networks is shown here. The loss function contains a scalar value b which acts as a margin. It is a hyperparameter. The objective is to keep the difference between the predictions of the two output layers at least b. It is shown that bipolar networks trained with this loss function are better at handling imbalance and learning from samples with all -1 labels. Subsequently, bipolar networks are extended to spiking networks, and to make it even better at mitigating imbalance, a focusing factor defined by FMM is used in the loss function. The focusing factor acts as a weighting term, helping the network incur very low loss values on samples on which it is more confident, effectively suppressing their contributions to learning. It can be viewed as a measure of the model's classification confidence. In addition, as different classes are imbalanced to different extent, the margin B is now a learnable vector of the same size as the output layer. So far, bipolar networks address the problem of data imbalance in multilabel learning to some extent. However, in continual multilabel learning, distribution shifts between tasks can be a problem. Tackling data imbalance along with distribution shifts in continual multilabel learning is more challenging. To address this problem, we developed the adaptive margin spiking neural networks. The key differences between the bipolar SNN and the adaptive margin SNN are highlighted here and in the figure shown on the left. The margin vector B is no longer a learnable parameter. Instead, it is predicted by one of the output layers for each sample. So, adaptive margin SNNs predict the logit at one output layer and the margin values at the other output layer. Therefore, the name adaptive margin SNNs. Following the same philosophy as in designing the loss function for bipolar SNNs, a focusing factor is included in the loss function. We choose the cosine similarity between the logits and the ground truth labels as the measure of the model's classification confidence. To test the hypothesis that the adaptive margin helps in better handling imbalance in continual multilabel learning, a baseline loss function with a similar focusing factor as adaptive margin SNNs is designed for training bipolar SNNs. The experimental settings adopted to test our methods are explained in this slide. We performed two sets of experiments, multilabel learning and continual multilabel learning. The sequential learning with model adaptation or SEA setup is used for continual multilabel learning. The model is trained on one task. Its size is grown to accommodate the classes from the next task. The weights of the model trained on the earlier task are copied over, and the newly added part is randomly initialized. The resulting bigger model is then trained on the new task. The setting proposed in the CIFDM paper is used for training and testing models for continual multilabel learning. For training, the dataset is divided into disjoint sets of samples and labels for each task. At the end of training, the model is tested in the combined mode, where all the labels seen up to a task are used for testing, along with all the samples in the test set. Model performance is evaluated using two versions of F1 scores, the imbalance weighted and the F1 score on the most imbalanced label. More details are provided in the references below. Details of hyperparameters and network sizes are mentioned in the paper. The table below shows the results of multilabel learning experiments. We compare the performance with bipolar SNNs and output layer ANNs. We use the correlation loss, asymmetric loss, and robust asymmetric loss for training the ANNs. Adaptive margin SNNs trained with the proposed loss function achieve the best imbalance-weighted F1 scores on almost all datasets. The highest gains over correlation loss are achieved for the plant dataset in case of the F1 score on the most imbalanced class and the G-negative dataset in case of the imbalance-weighted F1 score. Overall, adaptive margin SNNs show better imbalance handling capabilities than ANNs and bipolar SNNs. Continual multilabel learning experiments are done on three large datasets: eukaryote, birds, and human. The prefix E in the legends denotes the evolving architecture following the sequential learning with model adaptation setup. Models are evaluated in the combined mode as explained earlier. The plots show that adaptive margin SNNs do not incur much forgetting across tasks. Also, adaptive margin SNNs perform better than bipolar SNNs trained with the baseline loss function developed earlier. This supports the hypothesis that making the margin vector adaptive helps in better mitigating the data imbalance in continual multilabel learning. Finally, we conclude with a few key points. Adaptive margin SNNs achieve better imbalance mitigation in multilabel and continual multilabel learning. Adaptive margin SNNs show almost zero forgetting across tasks, and their adaptive nature helps them tackle the data imbalance in continual multilabel learning in a better way. In the future, we want to develop better loss functions and metrics for continual multilabel learning with SNNs and extend these to deep spiking networks for image datasets. That's all from my side for today's presentation. Thank you for your attention and have a nice day.